So we're going to look at ions. We're going to look at their electron configurations. We're also going to look at some magnetic properties and radii of ions and the energy required to make ions. A bunch of periodic trends here. So anions form when atoms gain electrons. Electrons can't gain electrons. Start over. Anions form when atoms gain electrons. So then what we do is we add electrons to the electron configuration. Cations form when an atom loses electrons, so we take them away, subtract them from the electron configuration for the atom. So to do an electron configuration for an ion, you start with the atom, and then you either add electrons or take them away. Well, adding them is pretty straightforward. Taking them away gets a little more complicated. For the main group cations, you're going to remove them in reverse of the filling order. So here's aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. That is the order in which they fill. And so when we make an aluminum ion, positive 3 charge, we have to take 3 electrons away. So we're going to remove the 3p electron. We get rid of this guy, and we're going to get rid of both of those guys. And that's what we've got left is the 1s2, 2s2, 2p6. This is the same electron configuration as which noble gas? That was a question. Which noble gas has this electron configuration? Neon. Yeah, sorry, I apparently confused you there. For the transition metals, you don't remove them in reverse order of filling necessarily. You take the valence electrons off first, and then you would go into the 3D or 4D or whatever. You'd go into the core electrons. So for iron, here's its electron configuration. There are 2 valence electrons. They're kind of hiding here in the middle. 4s2, and then there's 6 electrons in the 3D sublevel. When we make an ion, Fe2+, by removing 2 electrons, we don't take them out of the 3D. We get rid of these guys. You get rid of the valence electrons first. So we remove the 2 valence electrons. So there we have the Fe2+ ion. If we want to make the Fe3+ ion, then we take one of these d electrons, and so we've got the 3d5. So this iron ion, iron 3, ends up with an electron configuration of argon 3d5. This valence shell is empty then. Any questions? Have you ever wondered why some metals are attracted to magnets and others are not? It has to do with the electrons. So we say that an atom or an ion is paramagnetic if it has some unpaired electrons. Is iron attracted to magnets? Yeah, it is. Well, I guess this isn't the best example. That's an ion. Here's the iron atom. If we fill this in with the electrons that we took off, then we're going to have one of those d electrons back and these 2 guys back. So now we've got the iron atom. You see those 4 unpaired electrons? It's the unpaired electrons that cause it to be attracted or influenced by a magnetic field. Those unpaired electrons generate magnetic fields because of their spin. A charge spinning generates a magnetic field, and that will interact with other magnetic fields. A diamagnetic atom, or ion, has all of the electrons paired up, and this will be slightly repelled by a magnetic field. So metals that are not magnetic are diamagnetic. Everything's paired. Now, I have trouble remembering which is paramagnetic and which is diamagnetic. So, di is a prefix meaning two. So what I try to do is remember diamagnetic, all of its electrons are in groups of two. And then the other one is paramagnetic. So write the electron configuration and orbital diagram for each ion. Predict whether each will be paramagnetic or diamagnetic. It's hard to predict paramagnetism. There we go, paramagnetism from the electron configuration. It can be done, but it can be tricky. So we really want to look at orbital diagrams here too. So the noble gas, shorthand will suffice here. So for cobalt, what's the noble gas immediately before cobalt? That's argon. So argon, and then let's fill out that electron configuration. After argon, we're at potassium. That's in the fourth period. So that's 4s2. And then we're filling in the 3d level. And cobalt is 7, right? 7 over 6. Can't I count? 1. No, there's scandium over there.
Yeah,
7, right? The scandium's 21. That's the first one. And so cobalt's 27. That's the 7th one. Just checking because it's Monday, right? Now, is that one of those weird ones? The irregular electron configurations? They started with a C. No, it isn't. That was chromium and copper. Cobalt's fine. So if we look at the orbital diagram, that's what it's called. We've got 4s, and then we've got, oh, that didn't work out with my little boxes. Yeah, that's a mess. Okay, so that would be the electron configuration for cobalt atoms, right? But this is a cobalt ion. Are we adding 2 electrons or taking 2 away? We're taking 2 away. We're removing 2 negative charges, which gives us a positive. Stupid minus signs, right? So where are we going to take those electrons out of? We're going to take them out of the 4s. We're going to remove the valence electrons. So we'll take these guys out. So those are the electron configuration orbital diagram for cobalt-2 ion. Paramagnetic or diamagnetic? What'd she say about para and dia? Dia is 2, everything in 2s. We've got 3 unpaired electrons and a mooing balance. Doesn't that sound like a cow? I grew up in the Midwest. Yeah, one of the little toys. Okay, so this one's paramagnetic. That means that it would be attracted by a magnetic field. Okay, let's look at nitride ion. So for the noble gas electron configuration, we got helium. It doesn't save us much, but what the heck. And then after helium, we've got 2s2 and 2p, how many? 3. So that is nitrogen, the atom. Let's draw the orbital diagram. So this is 2s, and this is 2p, and we've got 2 electrons in there and 3 in here. That's nitrogen atom. So nitrogen ion, are we adding electrons, taking them away? Adding. So the electron configuration becomes ending in 2p6. And we have to add 3 electrons. 1, 2, 3. Paramagnetic or diamagnetic? Diamagnetic. All the electrons are in twos. So nitride ion is not attracted to magnetic fields. Any questions? We looked at trends in atomic radius. Now we're going to look at ionic radius. Cations are much smaller than neutral atoms. And this is because when you make a cation, you're taking valence electrons off. You're taking the outer level off and getting into the core. And so by removing that principal level, you're making them smaller. In addition to that, the effective nuclear charge has increased. I don't think I have a picture of that. No. So let's talk about it. Let's see. Let's look at magnesium. So if we look at magnesium, magnesium has how many electrons? 12. So 12 electrons total. How many valence electrons? 2 valence electrons. How many core electrons? 10 core electrons. So the effective nuclear charge for magnesium, the atom, is 12 minus 10, which equals 2. Right? That's the effective nuclear charge. Well, what about the magnesium ion? We lose those 2 valence electrons when it becomes an ion. So now we've got 10 electrons total. How many are valence? 8. Right? Because when you take those 2 electrons off, here let's look at, so it would be helium. No. Well, let's just do the whole thing. It's not that far. 2s2, sorry, 1s2, 2s2, 2p6, 3s2. Right? That's magnesium. Here's the 2 valence electrons. For the ion, we've got 1s2, 2s2, 2p6. These are the valence electrons now. So the effective nuclear charge for the ion, whoops, how many protons in the nucleus? Still 12. How many core electrons? 2. These are valence electrons now. So these core electrons, what's the effective nuclear charge? Plus 10. That's a lot bigger. Pulls it in. So we took a layer off, and what was left got pulled in. So this is showing us, where's magnesium? Here's magnesium atom, has a radius of 160 picometers. Magnesium ion, radius of 65 picometers. Less than half the size. It's a huge effect. This one's pretty easy to remember because if you peel something off, you expect the thing to get smaller, right? You peel the rind off of an orange, the radius gets smaller. But it actually gets a lot smaller than you might think. The opposite, making an anion, anions are larger than neutral atoms. That makes sense too, because you put more stuff on, you expect that it's maybe going to get bigger. The difference here, though, is more than you would expect. So we're adding electrons without changing the nucleus, and we get a lower effective nuclear charge. So not only are we adding electrons, but the effective nuclear charge is getting lower, and so it spreads out more. The difference from going to an atom to an anion is not as huge as for the cation, but it's still pretty big. So we always see that the anion is larger than the neutral atom. Any questions? Iso is a prefix that means the same. So isoelectronic means the same electrons. Isoelectric ions are ions of different elements that have the same number of electrons. They have the same electron configurations. So sulfide, chloride, potassium, and calcium, they all have 18 electrons, the same as argon. The electron configuration for all of these is the same as argon. The electrons are all arranged the same way. The number of protons is different. Sulfide, 16 protons, up to calcium with 20 protons. So the ion with the most protons is going to have the smallest radius because of the higher effective nuclear charge. Any questions? When you look at isoelectronic ions, the smallest one is the one with the most protons. They all have the same number of electrons. But calcium has 20 protons. Its radius is 99 picometers. As we go to fewer protons, the radius gets larger because it's a force of attraction between plus 16 or plus 20, and 20 is more attractive. So this gets pulled in, it's smaller. Any questions? Choose the larger atom or ion from each pair. There will be test questions like this. So, potassium atom or potassium ion, which is bigger? The atom, because when you make the ion, you take the valence electron off. You're peeling off that outer level, and so it gets smaller. So the atom is larger. Fluorine or fluoride, which is larger? The fluoride. The anion is bigger. You've added an electron, and the effective nuclear charge has also gone down. Calcium ion or chloride ion? Well, we have to look at these. So chloride and calcium. So calcium ion is going to be, calcium is argon 4s2, right? And when you make the ion, you take off those valence electrons. So this has the same electron configuration as argon. It's got 18 electrons. Chlorine was neon 2s2, 2p7. I'm sorry, 2p5. 2 plus 5 is 7. Making it an anion, we add an electron, so this is 2p6. That is now the same electron configuration as argon, 18 electrons. The electrons, the outside looks the same, but the inside's different. How many protons does a chloride ion have? 17. And how many protons does a calcium ion have? How many? 20. So 20 protons and 17 protons. That's what's attracting the electrons. So which is more attractive, 17 or 20? 20 is more attractive. That means that pulls the electrons in, so this one's smaller, that one's bigger. Okay? We're asked to choose the larger, so we're going to choose the chloride ion. So this can go back to the kids, dressing like each other in high school too. Why are some kids more popular, more attractive to other kids, even though they look the same on the outside? It's who they are on the inside, right? They're kind, they're friendly, right? There's this other person, they're equally attractive, but this person's a grump, right? And he'll stab you in the back when you aren't looking. Well, who are you more attracted to? The nice person, right?
Could you explain that one more time?
Which one? The science explanation or the students?
The science.
The science, okay, good. I don't want to back on. Okay, so calcium ion and chloride ion have the same number of electrons because calcium started with 20, but it lost 2, so now it's got 18. Chlorine started with 17, but it gained 1, so now it's got 18 electrons. So the electrons are the same. What's different is the number of protons in the nucleus. So chlorine has 17 protons, number 17 on the periodic table. Calcium has 20 protons, number 20 on the periodic table. So these have the same number of electrons. The electrons are the same. What's different is the nucleus. A positive 20 charge is going to have more attraction for electrons than a positive 17 charge. More attraction pulls those electrons in closer, making this one smaller and this one larger. Okay? Ionization energy. I kind of talk about atoms like they want to get rid of electrons. That's not actually true. It does require energy to pull electrons off of these ions. So the ionization energy is sometimes abbreviated IE. It's the energy needed to remove an electron from an atom or an ion in the gaseous state. We're not going to deal with absolute numbers, but we're going to talk about trends and positive and negative. So the ionization energy is always positive. So as the outside influence, you have to exert energy to get the electron off. So it's exothermic for the surroundings, it's endothermic for the atom. I think of it as, you've got this kid and he's got this sweatshirt or this dorky hat his mom made him wear. Okay, he'd kind of like to get rid of it, but he knows he's going to get into trouble if he just gives it to you. So you have to pay him for the hat, right? I'll give you $5 for that hat. So it's positive for the atom. The energy is positive for the atom. So this atom plus the ionization energy gives you the ion, and the electron now is loose. So here's the hat. We had to pay the atom to get it from him, but there we go. Now we have an ion. This +1 ion has more electrons, and we could take more electrons off. So here's our +1. Now we have to have more energy, another ionization. This is called the second ionization energy. So we're removing an electron from the +1 ion. So then we get a 2+ ion, and again, an electron that has come off. So maybe now we're taking his scarf too. I don't know. Any questions? So there are trends with the first ionization energy. As we go down a group, like here are the noble gases, helium, neon, argon, krypton, xenon. As we're going down the group, we see that the ionization energy decreases. Well, why is that? The valence electron, that's what's getting removed, is a valence electron. As you go down a group, helium's valence electrons are in n equals 1. Neon is n equals 2. Argon is 3, 4, and 5. Xenon's electron that's being removed is in the 5th principal level. That's farther from the nucleus than for helium. When something is farther away from the attractive charge, it's easier to remove. Okay, so that's why it's easier to take an electron from xenon. Okay, this gets into one of my politically incorrect, perhaps, illustrations. So I have 6 children. I have a friend who has 1 child, right? And so my kids are older now, but when they were all young and squirrely, imagine going to the big Fresno fair, which I never did because of this. So you go to the fair, and here I am with 6 kids. And here's my friend with 1 kid. You want to kidnap a child. Who are you going to target, me or my friend? Me. it's going to be a lot easier to take one of my 6. My attention is divided, and they're all over the place. We actually did temporarily lose a child at the Fresno Fair, but we got him back. He was just under a table. Nobody took him. But my friend only has one child. That child's going to be closer to mom, or mom's going to stay closer to the child. So if that helps you remember, you can learn from my almost missing child. So as you go down, ionization energy decreases. Ionization energy generally increases across a period, just like the radius. This trend is actually opposite of the radius. So as you get, no, wait a minute. Yeah, opposite. So going from helium to neon, atom gets larger, ionization energy decreases. It's easier to take an electron. As you're going across a period, the ionization energy increases as the radius decreases. Okay? So I just go back to, it's easier to snatch a kid from a large family than a small family. So you know the radius trend, and then you can figure out the ionization energy trend. Here's a graph showing actual numbers. And so we see, here's hydrogen. He's got a really high first ionization energy, because that's like my friend with the one kid. Hydrogen only has one electron. It's going to take a lot of energy to get that one away from him, right? And so as you go across, hydrogen's kind of up there, but look, lithium, beryllium, generally it's going up as you go. So on the basis of periodic trends, that means we're not looking at something like this, because I'm not going to give you that on a test, and you would not have to memorize this. Possibly could show up on a homework question, but I don't think so. Based on periodic. So why does it increase across the period? What happens to the size of the atom as we go across the period? It gets smaller, right? So smaller means the valence electron's closer to the nucleus, and so that makes it harder to take off than when it's farther away, okay? So tin or iodine, oops, I didn't draw enough boxes, so I'll just add one over here. There's tin and iodine. I start this by deciding which one's bigger, tin or iodine. As you go across, they get smaller, right? That means that tin is bigger, so this is larger size. Actually, we'll do this. That's the big one. This is the small one. Okay, so ionization energy is the energy expended to kidnap a child. Easier to kidnap a child from a big family or a small family? It's easier to kidnap a child from a big family, because sometimes they don't even remember how many kids they have in the first place. So we want higher first ionization energy. This would be low first ionization energy. This would be high. It is confusing, and that's why the only reliable way, if you ask me, to get these correct is to be able to reason it out. Did you have a question?
Can you look back at the other graph real fast?
This one?
Yeah. So if you're looking at it that way, you said
So-
it was the bigger, right?
Tin is the larger atom,
The larger atom.
and so its ionization energy is lower than iodine.
Okay.
Yeah.
And how exactly is it bigger atom?
Because as we go from tin to iodine, we're adding electrons in the same principal shell. So that would be the 5p sublevel is where the difference is between tin and iodine. That's roughly the same distance from the nucleus, but the effective nuclear charge is increasing. The number of core electrons is staying the same, but the charge on the nucleus is going up. And that's why it gets smaller. So we're looking at higher ionization energy would be iodine. Okay, calcium or strontium? So they look like this on the periodic table. Here's calcium, here's strontium. We're looking for higher first ionization energy. It's harder to steal a child from a small family, right? So which of these is smaller? Calcium. This is the smaller radius. Those electrons are closer to the nucleus. Remember, energy is proportional to the charges, Q1 and Q2, divided by the radius. Big radius makes this term small energy. So smaller radius is the higher ionization energy, it's the calcium. Carbon or phosphorus? Well, there's carbon, here's phosphorus. Carbon's smaller or larger than phosphorus? You can't really tell, right? Because the trends are going against each other. Going this way says radius is getting smaller. Going this way saying radius is getting bigger. And so when we go at this angle, they're conflicting. So we could, if we're forced to guess, we could, but we're just going to say not possible and go on with life. Okay, fluorine or sulfur? Okay, so these are also diagonal, but in the opposite way. Going across predicts getting smaller. Coming down predicts getting bigger, right? So sulfur is larger. Sulfur is larger. Fluorine is smaller in size. That's the radius. Big family, small family, harder to steal an electron. Small family, so it's going to be fluorine. Any questions? Then, of course, there have to be exceptions, right? So, in general, the ionization energy increases from left to right. But we see an exception between groups 2A and 3A. You see, the boron has a smaller first ionization energy than beryllium, and this bucks the trend. The reason for this is that boron is losing a 2p electron that is higher in energy, therefore less stable, and easier to remove. Boron's losing an s electron. So let's look at the orbital diagrams for boron and beryllium. So for boron, we're just going to look at the valence shell. Boron is going to have 2s and 2p. And it's got how many valence electrons? 3. So there's going to be 2 electrons in that 2s, and there'll be 1 here. And then for beryllium, there's the 2s, and it's got these 2 electrons. There is that 2p level there, just like, in a hotel, when there aren't guests staying in the rooms, are the rooms still there? Sure they are. They're available for guests to stay in, but they're not currently occupied. So these are empty motel rooms. So when we're removing an electron from boron, it's this 2p electron. Remember, because of electron interactions and shielding and on penetration and all that stuff, the 2p sublevel is higher in energy than the 2s sublevel. So taking this electron away requires less energy than taking one of these electrons away. Yes? Yeah. Okay, what? Okay, so think about the energy that these different sublevels have. So 2p is a higher energy sublevel. That makes it less stable. Okay, something that's high in energy is less stable. Think of the piano hanging outside the second floor window. That's not a very stable position. That's high potential energy. Piano sitting on the ground, much more stable. It's lower energy. Okay, so high energy is unstable. This electron is in a higher energy sublevel. It's easier to remove than the electron in this 2s sublevel. Okay? You know, if we're going to go with the kid analogy, this electron reminds me of Andrew, my Andrew, who is, he's pretty high energy and he's also extremely persistent. That's a nice way to say it. He's opinionated and stubborn. And then, so here you have a lower energy child who's maybe, you know, just like goes along with what the family needs to be doing. Well, which one's easier to take? That high energy one. And there have been days when you think, would it be such a bad thing if somebody took him? I think he'd be like the Dennis the Menace in the movie where those bums took Dennis and they brought him back, right? Because they drove him, he drove them bananas. But anyway, if that helps you, whatever. Don't call Children Protective Services on me. Beryllium will have a higher first ionization energy. That's not what we predict based on the trends. Based on the trends, as we go across, we expect the ionization energy to get larger. Boron should have a larger first ionization energy, but it doesn't. And that's because the electron that's being removed is less stable, and so it's easier. We have a picture here. Let's go back to this picture. So here's that glitch, right? Beryllium, 899, boron, 801 for the first ionization energy. This is not what we would expect based on the trend. We would expect this one to be higher than that one. And you see that there's a glitch pretty much all the way down. Not down here. Things get a little wonky down there. But even here on the fourth level, calcium's got a higher ionization energy than gallium. And again, it's because of the different sublevels. Okay, so we did that one. We've got another exception between groups 5A and 6A. Nitrogen's group 5A, oxygen's group 6A. We expect oxygen to have a higher ionization energy than nitrogen. The trend is that the ionization energy increases across. And the same for fluorine, phosphorus and sulfur, right? Sulfur is lower than phosphorus. That's not what we expect. Well, the reason for that can be found in looking at the orbital diagram. So here's nitrogen and here's oxygen. So nitrogen has its 2p sublevel half full. There's a bonus. There's an energy bonus for that. That's and there's this coupon at the hotel. If you've got it exactly half full, you get a discount. So oxygen has one more electron, and so its 2p sublevel is not exactly half full. If you take this one pesky electron away, then you get the bonus. So that's why oxygen has a lower ionization energy than nitrogen, instead of higher like we would expect. I am not going to grill you on these exceptions, but I want you to be aware of them and to understand how we can explain things like this with quantum mechanics. Any questions? Now this is a little more important to grasp, trends in successive ionization energies. So that's looking at the first, the second, the third ionization energy for the same atom. So let's look at sodium. So the first ionization energy, 496. So you took one electron off. The second ionization energy is a lot more. It's like, you already took one of my electrons. You want another one now? Well, I'm raising the price, right? So it goes up. Each electron goes up. But what we see is there's a big jump. For sodium, the big jump comes between the first and the second. For magnesium, it comes from the second to the third. The reason is that when you remove that, let's look at, so here's sodium and neon. Why can't I remember that? Here's the electron configuration for sodium. And what am I looking at? Magnesium, yeah. Here's the electron configuration for magnesium. So when we remove one electron from sodium, that's the valence electron. When you get that off, then sodium has a valence when you remove one electron from sodium, it has an electron configuration the same as a noble gas. That's what they're all kind of trying to get, right? So it's like, yay, I got there. When you try to take the second electron off, now you're screwing up the noble gas electron configuration. So it's going to be a lot harder. For magnesium, the first electron coming off, it's like, oh, okay, well, there's my valence electron. The second electron coming off, well, that's a valence electron also, and hey, now I've got the same I've got that noble gas electron configuration. You take the third one off and you're screwing that up, and that's why there's this huge jump. I mean, it's big, right? This one was 1450, and now it's over 7,000 kilojoules per mole. That's huge.
So each time there is only one electron?
Each ionization energy is removing one electron. Yeah. So removing the first electron, the second electron, the third electron, and you could conceivably just go successively take them all off. But we usually don't talk about more than the first few. It's meaningless. So here's a table. So here are the elements, and we're looking at first, second, third, fourth, fifth, sixth, and seventh ionization energies. So for sodium, 496, and then there's this big jump because this is removing the first core electron. Magnesium goes along. This is, roughly double that. And then huge jump because we're getting into the core electrons, and don't you mess with my core electrons. Aluminum is going up, it's going up, and then big jump. And so we see that there's this huge jump between removing the last valence electron and removing the first core electron. 27,000 kilojoules. That's a lot.